Hey guys, um, thanks everyone for joining today. We have Annika Thomas, who is pursuing a PhD at MIT under Jonathan Howe. She does a lot of robotic perception in multi-engine scenarios. We met her at IROS 23 and also at IROS 24 and came to know about her work and thought of inviting her. So yeah, Annika, take it away.
Cool. Well, as Adi said, my name is Annika. I'm a fourth year PhD student in the Aerospace Controls Lab at MIT. I primarily work on collaborative perception, multi-agent systems, and I'm excited today to talk about kind of this line of work that we've been doing. I'm gonna press OK so we don't have to look at that the whole time. On graph theoretic object-based localization in GPS-denied environments. So to start at kind of a high level with the collaborative SLAM problem or C-SLAM. In this problem setting, one of the things that's important to us is having consistent situational awareness for our multi-agent systems operating under a range of degraded communication, and degraded GPS environments. So some of the challenges that we face in this problem setting include that a lot of the time we have unstructured and unmapped environments. This causes a lot of place recognition or kind of different approaches that are based on urban fixtures to degrade. So we really want to be able to generalize to new problem settings. We also have an unknown initial transformation between agents. So we don't have any kind of initial guess. This basically makes the problem exponentially harder from a data association perspective. So we want things that are computationally efficient. We are operating under the assumption that we don't have GPS, so we can work indoors, underground, in other degraded conditions. And when we have multi-agent operations, we're assuming that we kind of have some disconnects, bandwidth constraints, etc. So the key technologies I'll be talking about today in the C-SLAM umbrella include frame alignment and data association between agents, as well as a little bit on collaborative trajectory estimation. Not my field of expertise, but we did work on something that incorporated some of our work, so I'll touch on that, and collaborative map fusion. So just in the multi-robot application sphere at a high level, there are a lot of people that are interested in these problems. Combined situational awareness for autonomous vehicles, search and rescue operations, assisted inventory management, smart factories, real-time perception for those cases, and these just subterranean exploration in general, especially for those GPS denied and communication degraded cases. So the two big things that we're looking at here, the constraints or challenges of this work is first off the GPS denied navigation and communication constraints. So a lot of the time GPS is not available for vehicle navigations. This could be due to blockages, indoor operations, or we just might not have access to GPS. So we have to rely on other sensors for our SLAM systems, inertial, LiDAR, etc. And these come with a host of their own issues. This can be limited field of view or range, high computation for onboard applications, and time delays. So we're looking at inter and intra robot loop closures. So loop closures within your own trajectory as well as between different agents. So these are important for correcting long-term errors and drift. There's also an opportunity for robots to benefit from information from other agents within their own perception. So challenges here, when we're looking at the object-based localization and mapping scenario, we're performing data association when we have noisy, ambiguous, and sometimes partial observations, so a lot of outliers. We have alternate viewpoints when we have different robots. So we're not thinking about kind of this place recognition based approach where you're looking at things from the same angle. So we get perceptual aliasing where things look different from different viewpoints. And we want representations that are suitable for both perception, so gathering information about the environment, as well as navigation. So knowing enough in order to avoid obstacles, navigate through the space. And the other thing I mentioned, communication challenges. When it comes to perception at a large scale, we have high communication costs. When it comes to building scale and city scale maps, we really get to the point where it's not feasible for real-time onboard operations to share that information. And we also have limited connectivity, bandwidth, and latency when sharing information between agents. So to get into the actual work today, I'm going to be talking about three kind of main topics under this graph theoretic data association framework. First of which I'll talk about global localization, and then, as I mentioned, a little bit on trajectory planning, and then I'll talk about actually applying these for loop closures and map sharing in real time on agents with multi-agent frame alignment. So starting with global localization. So the first work I'm going to talk about, what we presented at IROS in 2023. We were a finalist for the best paper in safety, security, and rescue robotics. This was the conference where I met Adi for the first time, so that might be why I'm here right now. And the work is called Global Localization in Unstructured Environments Using Semantic Object Maps Built from Various Viewpoints. So the objective of this framework is global localization. So that means that we have some pre-acquired map of the environment, and we're trying to figure out what our pose is inside of that pre-given map. And some challenges that arise in this global localization setting. First off, we have environment changes. So our pre-acquired map, our reference map, could look pretty different from the space that we're at now. It could be a different time of day. It could be years in the future. So objects and the underlying environment could change. And we could have movement from dynamic objects, from people, bikes, cars, things that aren't going to look the same over time. We also have challenges related to perceptual aliasing from different viewpoints. So we do experiments on aerial to aerial maps, ground to ground maps, and aerial to ground maps. And we want to reduce drift. That's one of the core reasons that we do global localization. So the overview is the pipeline is we start with a reference map of objects. This is using the Kitty dataset. And blue dots here refer to parking spots. So this is from a satellite image. Next, a vehicle explores the environment, creates its own map of objects. In this case, the red dots are cars that are extracted from using YOLO, which cars are indicators of parking spaces. I highlight parking spaces because these are underlying things that don't change, even though the presence of cars do change. So we use a geometric data association process in order to align the reference map and the local map. And then we test those registrations using some heuristics. And once we have one registration that's accepted, so one global localization event, we can continually leverage that history to replace it with a better guided relocalization process. So in this process, in this pipeline, we're using semantic information. One of the main reasons we're doing that in this global localization after a lot of time has passed, we want to make sure that our objects can be continually and consistently identified when we have different lighting differences and seasonal changes. It also can provide us useful information about the context of the environment for other information sharing or potential downstream applications. And these maps are incredibly compact, so they can be shared and processed on board in real time. We're just using a 3D centroid point and a semantic class for each object. In the Kitty dataset, we use parking spots. The reason we do this is because we want robustness to outliers. This helps us broaden applications beyond just urban-centric using this pipeline. We can identify damage after natural disasters or in cases where we only have access to old environment data. We can handle high outlier regimes. We use cars as indicators of parking spots because they can be identified from different viewpoints. So if you think of in an urban-centric setting, if you were to use something like a stop sign as an object within the scene, if you're flying a drone over top, the stop sign's not going to look the same or be as easily able to be identified in the scene versus cars can be identified from the aerial and ground viewpoint easily. Also, if we were to rely on the presence of buildings or roads, this restricts our framework to urban environments, and we also show the performance of this and want it to operate in unstructured environments. So getting a little bit into the data association process, we have a reference map and a local map. So if we have an initial guess, you have probably heard of ICP, great approach for that if we have a good initial guess. But in the case where we don't have an initial guess, this data association problem gets much more challenging. So our approach here is to use a graph theoretic data association process. So again, our vehicle maps consist of a 3D object centroid and class of each object within the map. Our optimization problem is to find the largest set of geometrically consistent associations using the parallel maximum clip. So on the left side here, the blue dots, again, those are referring to our reference map, and the red dots are referring to our local map. So we have a bunch of initial putative associations. Those are A1 through A5, and we create this geometric consistency graph. That's the black one on the, I guess, in the middle there. So all of the nodes in that graph represent associations, and the edges between them show whether or not those associations are geometrically consistent. So you can see that A1, A2, and A4 are consistent with one another, so that's why they're connected in the graph. So the optimization problem is to find the maximum clip of consistent associations. So the actual pipeline accepts registration based on 3 criteria. First of which is the number of inliers in that optimization problem. We have more inliers, we're more likely to have an accurate representation or an accurate registration. That's kind of the most intuitive one. The next is the average distance to the nearest neighbor. So this is how well the map as a whole aligns with the reference map. And for a visualization of what that looks like, down in the bottom left, we have 2 potential associations that have the same number of inliers, but using the nearest neighbor average distance, it helps get rid of the potential registration that's circled in red. That incorrect one you can see versus the correct is circled in green. And the third criteria we use to accept registrations is the similarity between our current and candidate transformations. So once we already have at least one localization event, this triggers a guided relocalization kind of module, where if we have large differences between new and previous registrations, they're less likely to be accurate. So in our experiments, we localize within 2 different reference maps. We have a LiDAR map that's taken from a ground view, so this is changing our modality. And we have an aerial map that was taken several years beforehand. So this is a viewpoint difference and also shows kind of the robustness to changes over time. So just to give a visual of what this looks like in the kitty data set, you can see we're extracting cars using YOLO, and there was the localization event. So we're driving around and using that kind of underlying geometric structure, we're able to figure out where we are. So again, testing on 2 reference maps, here's some more quantifiable results. We've got LiDARs, which is a ground view same environment, and a reference map taken from a Google satellite image. So this is highly changed over time. Our parking spaces are our classes. And in this case, our registration error is defined as the pose error at the time of each localization event. The other thing that we wanted to test was kind of an ablation study on this guided relocalization module. So to demonstrate the effectiveness of that guided relocalization, we test the difference between the position error of using just OrbSlam and using OrbSlam with guided relocalization. So the result here is you can see that using the position error with that guided relocalization is about half the error as without it. And if you're curious about those spikes in the graph, because most people usually are, that happens when our vehicle moves around the corner. So there's just a lot of OrbSlam error in those positions anyway. We also, in addition to the urban environment, test this in an unstructured environment. So this is with the Catwick Beach Planetary Rover data set. We have 3 different sizes of artificial rocks on the beach. So small, medium, large, we use those as the semantic classes of the objects. So identified rocks are classified by their size, and we split these traverses just into smaller segments to perform that global localization and test in a lot of different cases. So this is a picture of traverse 3, 103 meters, and then traverses 1 and 2 are shown here. We use traverses 1 and 2 as a way of testing view invariance in the pipeline. So this is an out and back trajectory. So we split it at the halfway point, create a reference map from the first half, and then localize within the second half. So this helps us test kind of the view invariance is a case in which more feature-based approaches would fail because things look really different from the opposite viewpoints. So using objects and geometric consistency helps enable that view invariance. So the key takeaways from this work, it's a pipeline for global localization and guided relocalization of the vehicles posed in unstructured and urban environments using maps from various viewpoints. So we use the Catwick data set and the benchmark, and we show view invariance and robustness to high numbers of outliers. So this is a couple years old, but it really was a foundational work that helped inspire a lot of the next direction of what we've been working on in the lab, is using this underlying graph theoretic approach, which looks at the geometric structure of the environment, tends to be really, really good in cases where we have high outlier regimes.
Can I ask a quick question or you prefer later?
Sure, yeah, let's do it.
So I had read the paper. I couldn't wrap my head around the kitty example. So you said that there's seasonal change, or like there's a very long-term change.
So the kind of long-term change is due to kind of the satellite image being taken a couple years beforehand, and there's actually been a bit of construction, the roads that are closed.
Sure. I guess like in that example, you have cars that you're using as like your object markers.
Yeah.
And so you kind of still find that this graph theoretic approach is better, even though cars like completely change.
Yeah, because we are just extracting basically, that's why I wanted to emphasize that the class is more parking spots than cars. So cars are extracted to indicate parking spots, but we're not looking at like the cars that are driving around. These are kind of small neighborhood streets, but it's a good question. A lot of people have that question, so. But that kind of helps lead me into the next work. One of the big limitations of that global localization approach is that we're using YOLO to extract a set number of object classes. So in order to work in unstructured and new environments, we really wanted to approach this without having to predefine that set of classes that we expect to see. So this inspired SOS Match, which is segmentation for open set robust correspondence search and robot localization in unstructured environments. So we are operating in the open set case here. Again, that means we aren't defining a preset number of classes that we expect to see. And some of the challenges that we face, again, we're not working with GPS assumption here. So when we have infrastructure-based methods and we're operating in new environments, we can't always rely on the presence of GPS. We also want to have robustness to environmental variations. This is definitely a much more extreme case. We're working with this data set on the right here, so you can see that there are big environmental variations over time. We also really value having compact maps so that we can enable the use of multi-agent map sharing and real-time processing. So SOS Match had 2 novel components, the first of which is this front-end mapping pipeline. So this is using a combination of the vehicle's odometry sensor and camera images in order to create a vehicle map for localization. This is using segment anything model, so we're operating in the open set case. We tried, before SAM came out, we tried training some classifiers in order to extract the trees within these aerial drone images. And we basically could not get it to work unless we really overfit on the data sets. So it was really nice when SAM came out and kind of enabled that object extraction. And the next part of this is a frame alignment pipeline. So this basically is one of those data association problems that scales exponentially as it gets bigger. So we also have kind of a sliding window based approach in order to make that tractable for onboard localization. So this may look a bit similar to the other approach. In this case, rather than just the 3D or the 3D object centroid in the semantic class, we're using the size of the objects in order to form kind of this same graph theoretic data association. But one of the big differences here is we are finding, instead of the parallel maximum click, we're finding the maximum densest edge weighted click. So now this graph up in the top right has this S of X function, which defines the weight of each of those associations. So just because I think this is really cool, I decided to go a little bit more in depth on the data association. The objects are points in this case. The associations U1 through U5 are compared for the compatibility, and we build this compatibility graph. And we're working with this affinity matrix M, where the rows and columns are the association numbers. So if two of the associations are consistent with one another in a binary case, that is going to be a 1 in that entry, versus if they are not consistent with one another, it'll be a 0. And you can see that down the diagonal, it's all 1s, because intuitively these associations are consistent with themselves. So in this case, U1, 2, and 4 are consistent inliers, but instead of just looking at the binary case, something different that we do in SOS match is we introduce the weighted edges. So the M matrix in the bottom right is all 1s and 0s, but in SOS match, we're actually looking at weighted combinations of that, which helps guide the localization process.
So we can use us about the size of the graph, and so this is a biset problem with weights on each edge, and want to find the maximize some value of the matching block.
Yeah, so it's the maximum densest edge weighted click of that graph in the top right. So we're basically maximizing now incorporating kind of the weights of the associations into that optimization problem. Instead of just maximizing the number of things within the click, we're maximizing, I guess, that expression in the middle there. And we're defining that the consistency of those associations based on kind of a size heuristic that we talk about more in the paper.
So what about the size of the nodes?
The size of the nodes?
Edges.
Oh, like how many
Yeah.
are, okay, yeah, so that's part of the sliding window based approach, so it depends on the size of the map. We are testing over about a 3.5 kilometer trajectory, so we have a few hundred of the associations or potential objects within the map that could be associated. So what we do is basically take a subset of that map and then use a sliding window for all associations across the rest. In order to make that not take forever. So getting a little bit into the actual experiments that we did, we released the BotFix seasonal data set. I mentioned it's 3.5 kilometers, and a lot of it is over really dense forested regions. So this makes it a pretty challenging problem. We are looking at not just following the same trajectory, but also the places in which we overlap. So that's loop closures within its own map, as well as looking at kind of localizing within a different map from a different viewpoint, which gets really challenging in the middle of a forest. So for the experiments, we compare the pipeline's precision and recall, which we define in kind of a like a place recognition based approach to defining precision recall. So we have places that are referred to as being the same, and we have map size, search time, and we look at the view invariance from different viewpoints. And we look at 5 monocular vision-based approaches. So we have 2 feature-based approaches, just classical approaches using SIFT and ORB features with RAMSAC for geometric filtering. We look at a global descriptor-based approach, state-of-the-art, AnyLock, very nicely done. Unfortunately, this is a really challenging problem setting, so it doesn't work super well here. And we look at 2 learning-based feature approaches, SuperPoint and SuperGlue, and Lofter. So here are the precision and recall cases. So we have the blue line, and we perform as well as or better than all of the other methods in 3 of the cases. The only method that outperforms us is SuperPoint and SuperGlue in the winter setting. And so something we wanted to look at as well was not just this precision and recall over the whole graph, but how this varies when we are looking at loop closures from different directions as well. So on the left here, we have the average F1 score in the cases where you're following the same direction and the more challenging different direction viewpoints. The left bars for all of these baselines are the same direction, and the right bars are the different direction. So you can see that all of the methods perform worse in that more challenging setting, to be expected, but the learning-based methods, namely SuperPoint and SuperGlue, which is pretty on par with a lot of our performance or better in one of those cases, really struggles to generalize to those new viewpoints. And one other test that we did was just evaluating the search time, so the time it takes to localize, as well as the map sizes themselves. So in terms of search time, we're running pretty quickly. AnyLock is faster. It's using cosine similarity, which runs really quickly for that kind of map matching step. And our map sizes are much smaller than all of the rest of the maps. And I want to say that this is another example of the Botvik seasonal data set. We're really flying over just a lot of dense forested areas. And if you're interested in this type of problem, we did release this data set with a data loader. Could be interesting for some place recognition problems. So yeah, that was SOS Match, presented this last year at IROS. So segmentation as an object-based mapping pipeline. So next, I want to talk a little bit about the kind of multi-agent trajectory planning work. This is something that we presented last year that Koda Kondo in our lab led. And my kind of piece in this was the first time that we implemented SOS Match for frame alignment on board in real-time applications. So PUMA is a perception and uncertainty-aware multi-agent planner. We are performing localization on board in order to help mitigate drift that occurs over time. And the approach of PUMA is within the actual trajectory planner is it propagates location uncertainty of obstacles. It also tracks obstacles and plans to avoid them based on their trajectory as well as the agent's own trajectory. So it plans trajectories that can help observe obstacles with respect to direction of motion. And just to give an example of what this means, some previous work in the lab was really good at obstacle tracking. So it plans trajectories to always be looking at obstacles. But if that obstacle were to move towards the agent, then that agent would just move backwards with basically no regard for what's behind it. So it could potentially lead to some collisions, which is what inspired this work. So PUMA is a fully decentralized distributed planner that helps reduce uncertainty in the environment, better understanding obstacle motion, and it balances exploitation and exploration. So I mentioned before, Panther is that work that just focuses on obstacle tracking. So this could lead to collision issues with unknown obstacles.
What do you mean unknown obstacles?
So when you're flying in an environment where you don't see what's behind you, I mean, like if there were potentially an obstacle behind you. So if your trajectory is planned to move backwards, but you're tracking the object in front of you, you're not going to turn around to look behind you first. So yeah, good question. And the other part of this that I worked a bit more on is onboard generating segmentation masks from those images to create a sparse map. So this can be used on board between multiple agents to share and align their maps with one another. This is some of our testing against Panther. While we look at an object with Puma a smaller percent of the time, because we are also looking at different areas within the trajectory, like that example I mentioned where you move backwards, you might need to turn around to see what's behind you before you move backwards. Panther, the previous work, would be looking at it all the time, but yeah, mitigating that issue. So to show some simulations of what this looks like, we have two agents in this case and a dynamically moving obstacle in the middle. In kind of the top middle, you can see the segmentation-based maps that they're creating and sharing with one another, and they plan their trajectories to avoid that obstacle, tracking its motion, and they treat other agents in the map as obstacles as well to avoid one another. And we test this not just in simulation, but with hardware experiments. So this is basically the same thing as I described. We have those onboard images from the drones. We're undistorting them and creating object-based maps. So the last thing that I want to talk about today is implementing these in multi-agent frame alignment settings. So I'm not going to talk too much about this work because we're working on it right now, but I'm collaborating with a group at CU Boulder for a kind of multi-agent collaborative SLAM system that takes raw LiDAR scans, and we've trained a neural network to transform them into OpenStreetMap style maps, which are much more compact, and we can use them for this graph theoretic data association. So we're looking at points here, sparser maps, and we're able to align maps with one another. But the main reason that I wanted to mention this today, since it's not out yet, you can look out for it in the next few weeks, but we also are releasing a very large multi-robot campus-wide data set at CU Boulder. So this has raw LiDAR scans, images, RGB images, as well as full annotations of the point clouds within the maps. So this could also be potentially useful if you're interested in multi-robot applications. So the last work that I'm going to talk about today, we submitted to RSS. So it's available now as a preprint. And this is the most recent extension from the SOS match segmentation-based mapping and alignment. So this is Roman OpenSet object map alignment for robust view invariant global localization. So the first thing that Roman does is extends SOS match, no longer to just working bird's eye view from drones, but we're now working ground view from robots. We're incorporating RGB images, so it's not monocular cases, but something I want to point out about this kind of object-based mapping approaches, you may notice that we're not mapping the people. We can reject kind of undesirable objects in real time from those maps. So that's what we're doing there. So we've been working with this kind of pairwise geometric consistency approach to the data association problem, but in some cases, just having that geometric consistency is not enough information in kind of ambiguous settings. So this kind of raised the question from SOS match, we have this really, really compact maps. So what more information can we add to handle these challenging settings? So Roman begins to answer this. We're looking at the direction of gravity, object geometry, and semantic information and incorporating it into the underlying optimization problem.
I have a clarification question. So what is, by global localization, are you still matching it to the bird's eye view?
So,
Or like, what are you matching?
it's a great question. We actually have this discussion all the time on kind of the difference of localization versus multi-agent frame alignment, because the underlying data association problem is the same. The idea of calling it global localization is I have a pre-acquired map and I want to localize within it. When we use global localization in this case, we're talking about a map that was acquired by a different robot, in a previous setting. In the other work, it referred to like the aerial map, like you mentioned. The reason that I put this work under the multi-agent frame alignment umbrella is because of the results that I want to show, because that's kind of one of the big cases. It's more of a framing thing, but the underlying approach is pretty similar.
So like the map representation you're matching to, is that like a LiDAR map or like?
So in the first case, we were looking at LiDAR maps and aerial maps. In this case, we are matching to a pre-acquired map that's using the same pipeline in order to create it. So the maps that, look like, well, I guess this is kind of easier to see in real time. The maps that are kind of these segmentation, voxelized, object-based maps are what we're comparing to in this work. So we talked before about changing the M matrix in order to incorporate that size heuristic. In Roman, we're doing it a little bit more intelligently. We did a lot of testing of the best ways to incorporate this information and decided to, well, I'll get a little bit into the math, but we are doing this maximum densest edge weighted click again, based on this M matrix. So the overview of Roman and how it works, we're taking RGB images this time, and we extract observations from the environment using fast SAM instead of segment anything because it's faster, and clip in order to get object semantic embeddings. We pass those as well as VIO into our module that generates segment maps. We first reject undesirable segments, so those are like dynamic objects like people. We perform frame-to-frame data association, merge segments, and then we create these submaps. Then we pass those submaps into the data association module, which uses the object semantics, shape attributes, and prior information about the direction of gravity to perform that frame alignment. So getting a little bit into those three components, first off, we have gravity. These images are taken from the Chimera multi-data set, which we evaluate the performance on. We are effectively decoupling the computations in the XY plane with those along the Z axis in order to kind of get rid of the potential associations that have large vertical differences between objects. So this right side shows what would be on the top, that would be a promoted association with a higher score, and it would be a penalized association on the bottom with a lower score. We also incorporate shape information about these objects with a 4-dimensional vector that incorporates a 3D bounding box around objects, as well as linearity, planarity, and scattering attributes that we get with principal component analysis. So on the right side here, we can see we have objects that have the same semantic class. They're both bushes, but on the bottom side, we have a really long bush. So this would help penalize that association. And the last part that we incorporate is semantic information as well. So again, we're trying to operate in open set settings. So we don't want to describe or give the pipeline a preset list of classes ahead of time. So we use the raw clip embeddings of those objects for this kind of semantic information. And we're just finding the cosine similarity to get that metric. So testing this, first off, we use the Chimera multi-data set. Just curious, who here is familiar with Chimera multi-data set? Okay, it's basically a campus-wide ground rover data set of a bunch of different robots driving around, all the different colors here. There's 6 different robots, and it spans, I think, like a half to 2/3 of a mile in different directions. So we split this into a couple of different cases. We kind of have our easy single robot case, which we're performing roughly the same as OrbSlam and Fair Multi. And then we get into the medium and more challenging cases, which is really what Roman was designed for, in order to handle different viewpoint variations. And we perform much better than baselines in those cases. And just to show what we're actually looking at on the right side here, the big method for loop closure that we're comparing against is visual bag of words, so visual features. And the lime green lines in this case are the places in which we have loop closures. So just to point your attention to the middle there, you can see on the left side with Roman, we have much more loop closures in those challenging different direction cases. We also test this in an outdoor unstructured environment with a data set that we took over at West Point. So in these challenging opposite viewpoint cases, over on the far right, you can see that Roman on the top is successfully aligning maps between different agents versus using visual loop closures on the bottom, fails to do so in those challenging settings. You can see that they're not aligned. So that's all I wanted to talk about today. Basically, this line of work is inspired by the idea that if we're looking at the underlying geometric structure of the environment, that helps us with issues like perceptual aliasing and yeah, using those object-based approaches, especially with some new learning-based front ends where we can extract information in new open set settings, enables us to effectively perform localization. So thanks.